Today I want to move away from entanglement. I want to move away from spin entirely. Let me bring up some slides. What I want to do is make the jump from thinking about spin in terms of linear algebra to thinking about a particle in quantum mechanics from the perspective of functions. And this jump is one that is very rarely dealt with directly in undergraduate courses. It's often assumed that you'll either come down the functional version and then sort of pick up what's going on when people start using matrices and vectors, or you'll come down the matrix and vector route and then suddenly work out what's going on when people start putting in functions without actually addressing how these two pieces of what appear to be very separate approaches, Schrodinger approach and Heisenberg approach, actually have a lot of common ground in the middle and how they sort of fit together. And so, from a conceptual perspective, today's lecture is going to be slightly difficult in the sense there's not just something that you just take and apply and learn. You kind of have to think about how pictures fit together in some way to make the subject. But I really like to get to this one early because it changes the way you think about all the quantum mechanics that you learn after it. You suddenly start to understand that there's not really two separate pictures here. It's kind of just looking at different sides of a common coin. So where I need to start on this is with something that I often like to point out to undergraduate students, which is that physicists often are just bad mathematicians. What I mean by bad mathematicians is that often we come through as undergraduates and we learn all the frameworks of mathematics in very detailed ways. So most physics undergraduates will take a minor or a second major in maths. They will go through and prove all the things that we know of the axioms of mathematics, all the proofs, all the theorems. And then what we tend to do is take what we know from that and operate in a slightly more relaxed space where we know that essentially we're not being completely pure with the maths, but we're not so far away from being pure that we're doing stuff that's wrong. Okay. My favorite example for this is often you'll float around in physics and people will say something like 1 over 0 is infinity. And if you take it from a pure mathematical perspective, you go, no, 1 over 0 is not defined. What you can say is that the limit of 1 over x as x goes to 0 will head towards infinity, right? Nonetheless, you know that that's true, but it's close enough to be loose enough that you can kind of, for a lot of intents and purposes, just go 1 over 0 is infinity and treat it more or less like that, okay? And so what you're really doing is just loosening up the edges a little bit, knowing that you kind of have this safety net of sort of firmness of maths behind you. And that's something that we kind of do in quantum mechanics in moving from between the two different approaches. We know that there is actually a way to prove all this sort of stuff in the limiting extremes. And then you can sort of operate in this middle ground knowing that you have that maths as a safety net. And I often like to do it this way because it saves me having to spend sort of, a dozen lectures proving all the background mathematics to this. And I can let you just know that that's going to be in your maths courses somewhere. That underpins what we're going to do. And we're going to take a sort of a slightly loosish transition here, knowing that we have that safety net behind us that makes the mathematics that we're doing right, even though we're not thinking about it in the purest way. Okay? So where I'm going to take you in this lecture is to a place where we're basically going to treat functions as infinite vectors. Okay? So where I want to start with this is you'll remember way back in the early parts of the course, we started to deal with our electron with an angular momentum. And as you remember, electron has spin up, spin down. So it'd have, it's a spin half particle, so it's plus a half, minus a half. And we abstracted away that h bar over 2, or what we call a half, back to just +1 and -1. And so we built a mathematical framework from this where we basically combined linear algebra with complex vector spaces to start to be able to make predictions about how that system's going to behave. And it works quite well. back when we set up that mathematical framework, we had a whole bunch of axioms that held, right? So the idea that the sum of any two vectors is a vector, the addition of vectors is commutative, there's a zero vector, there's a minus vector. If you take a vector and multiply it by a complex number, you get another complex, so you get another vector, and that operation is linear, okay? All these things are basically rules that we have to make the vector space that we work in well behaved, okay? The interesting thing that happens here, and you'll know this from your maths courses, is that every single one of these properties holds for functions as well, okay? So in a sense, the well-behavedness of our complex vector space for dealing with physical problem like quantum mechanics is also provided by functions in a sense, right? They're just as well behaved, and so we could imagine possibly using them to deal with quantum mechanics. And what you'll find is that you can use functions to deal with quantum mechanics in the same way that you can use vectors to deal with quantum mechanics. And what I want to show is that there's, in a sense, we see it as a seamless transition between the two depending on the situation that we're dealing with, okay? So let's start down this path of making this logical transition from a vector-based system to a function-based system. So the system we've dealt with most prominently so far has been the electron spin, right? There's two possible observables. So the thing that we would measure in that system would be the component of the angular momentum along the z-axis, with two outcomes. One is spin up, and the other is spin down, right? Plus a half and minus a half. The way we represent that mathematically is we have vectors that describe the state, they're 2 by 1, and we have operators that operate on those vectors that are 2 by 2 matrices, okay? So we've already foreshadowed this a little bit, but let me go there properly now. You can imagine that we might have 3 observables for a system, okay? This would be a particle with, say, spin of 1. And to give you an example of that, you would have a photon, okay? So if you think to your first year courses, you learn about light having polarization, like linearly polarized. There's another 2 polarizations that light can have, which is a sort of left turning and a right turning circular polarization. And those basically correspond at the single photon level to a particle with a spin of 1. So a spin plus 1 up, a spin of 0, and a spin of minus 1, okay, which is basically your circularly polarized one direction, circularly polarized the other direction, and just linear polarized light. There, what you would do to handle that would be you would have vectors that are 3 by 1, you would have operators that are 3 by 3, and all the same apparatus that you use for quantum mechanics for your spin half particle, like an electron, works for a spin 1 particle, like a photon, okay? You can take that one step further. So now imagine you've got a system that's got 4 observables. So you might have a system where you would have what we call spin 3 halves. So you'd have a spin of 3 halves up, a spin of a half up, a spin of a half minus, and a spin of 3 halves minus or 3 halves down, okay? One way to make this is actually to take a semiconductor, so you've basically got a solid with a whole sea of electrons in it, and instead of considering the electrons, what you do is you consider the holes. So the holes are kind of like a antiparticle for electrons in a semiconductor, and basically they're the absence of an electron that can flow in the opposite direction with the opposite charge. Positively charged particle will go in the opposite direction to electron. They can behave in certain circumstances like they have a spin of 3 halves, and so of course then you've got 3 halves up, half down, minus 3 halves as well. And there you would have vectors that are 4 by 1 and operators that are 4 by 4. And you can handle them in exactly the same way that you handle an electron with spin half, except you get more interesting behavior popping out. You can take this further. So if you stick around in quantum mechanics long enough, you'll see higher systems. So, you know, there are certain places where you use 8 by 8 matrices for some problems, and larger and larger and larger. And you can even take this to an interesting limit of trying to look at, for example, atomic structure or an electron confined in a box where you've got a large number of energy levels. So for your atomic structure, it's progressively further and further away from the nucleus, or higher and higher energy of sort of your orbit. In a particle in a box, it's higher and higher energy levels. And there, what you can do is go, well, each of my energy levels is an observable. Each of them has its own particular eigenstate and eigenvalue. And so I have n of those. And so what I can do is make vectors with n elements in them and operators that are n by n. And you can imagine the bigger the system gets in terms of the amount of observables you have, the more complicated the vectors and operators you need to deal with it. Okay. Eventually, you get to the limit where you've got basically an infinite number of observables. Okay, so you can imagine, like a system where you've got energy levels as your observables, and you might have an infinite number of energy levels in there. So you'd have an infinite number of rows in your vector and an infinite number of rows and columns in your operators. And at that point, you can, in principle, end up at the place where you see your vector, which now has an infinite number of numbers in it, more or less like what you have in a function, right? If you think about a function, what you've got is you've got some x-axis. It's more or less continuous in the sense that, there's an infinitely small distance between all of the particular positions on that axis. Each of them has a value associated with it, and that big set of numbers, whether you see it as a vector with a whole pile of elements in it, or you just see it as a function with a whole pile of numbers running along some axis, there's not really a very massive difference between the two. Okay. And so what we do, at least as far as the physics is concerned, and I'll let the mathematicians prove the aspects of this for you in other courses, is you can more or less make the step from thinking about vectors to thinking about functions in more or less the same way. Okay, and so this infinite dimensional limit is more or less what's truly Hilbert about the Hilbert space, in the sense that if you look back at the history of Hilbert spaces, what David Hilbert was actually looking at was functions and not really vectors. Okay. All right, so we've kind of made this jump just by adding more and more to our system. And if you kind of follow this idea, you realize that the matrix version of quantum mechanics and the Schrodinger sort of wave function version of quantum mechanics are kind of one and the same thing, just in opposite extremes of the limiting number of observables you have in the system, right? The matrix mechanics version that we see with spin is just, we've got two observables. And for the functional version where we've got wave functions, we've essentially got an infinite number of observables. Let's put some context to this functional version for a second. I want you to think about a particle traveling along some x-axis, right? It'll have some momentum p. It's a problem that you've probably seen very quickly in your first year courses, because hopefully you've done uncertainty principle, at least as a sort of a first look. So delta p, delta x is greater than or equal to h bar over 2. So you have this idea that, you've got some particles traveling along with some momentum p. It'll have some position x we can measure at any particular time. And we have some relationship that governs how well we can know the position relative to how well we can know the momentum. Okay, we'll come back to the relationships between position and momentum later on. I just want to focus for the moment on position, right? We have position as in where the particle is, and that would be equivalent to, in our spin system, asking the question of what is the angular momentum component along the z-axis. Okay, so these are sort of what your thing that you want to measure is. Your observables here are, if you think back to your angular momentum, there's two possible observable outcomes. One is the spin points up, the other is the spin points down. Okay, they're your two. Here, if you think about where your position is along the axis, you would imagine that actually there's an infinite number of observables, because there's the observation that it's at the position 0, there's the observation that it's at position 1, observation that it's at x equals 2, x equals 3, so forth. And you can chop that arbitrarily finely, right? There's the possibility that you see it at x equals 0.1, there's the possibility you see it at x equals 0.01, and so forth, chopped all the way through, right? If you think back to your spin, there's now two eigen vectors and two eigenvalues, right? One of them is spin up with +1, and one of them is spin down with -1. And if you now think back to your particle on an axis, every single one of these observable outcomes is essentially an eigenvalue. Okay, so really all we're doing in this limit of infinite dimensions is saying that every single position that we can have along this axis is an eigenvalue of some operator that determines the position of the particle. Okay, so in the second half of this lecture, what we'll do is we'll come back and we'll work out what this x operator looks like. We'll work out what the p operator looks like as well, and show that you can basically take the idea of your spin, expand it up to an infinite number of dimensions, and just pop out operators for position and momentum that in next week's part of the course I'll show you just naturally pop out an uncertainty principle for you. Okay. All right, so once you've got this idea, a lot of quantum mechanics makes sense because you sort of see the whole thing fitting together under one framework that's really just an extension on that simple linear algebra based model for spin up and spin down, just expanded to a very big system. It also explains to you sort of where it comes from a little bit easier too. So let's formalize this a little bit because what I've done so far is really just sort of wave my hands around and explain what's going on. So what we're going to do, just to put this in a little bit of a more mathematical context, is come back to our idea of some sort of observable, random observable, doesn't matter what it is, L, that has eigenvalues lambda at eigenvectors lambda. Okay, and so we've sort of been using this as a proxy for any particular observable we've had so far. If you remember back to around lecture 4 or lecture 5, we showed a relation that looks like this, that we sort of connected to completeness and the completeness relation, right? The idea here is that for any arbitrary state A, what we have is the sum or a linear combination of the basis vectors or the eigenvectors for that system with some complex prefactor that ultimately determines the probability. Okay, so if you think about this in terms of our spin up, spin down, what we would have is some state A that would be alpha up times the up eigenstate plus alpha down times the down eigenstate, right? Two possible states, the linear combination is kind of simple. And there what we would do is take a sort of, like inner products or projection operators to get us probabilities of whether we would measure up or down that would then be related to these prefactors in here, alpha up and alpha down, okay? Either as alpha up star or alpha down star. So now we're going from our two observable systems, spin up, spin down, to let's imagine something that's got a little more sort of possible number of discrete states. Let's say 100,000 or something, right? What you could imagine is that, well, the name at the front A is kind of arbitrary, right? So what we're going to do is we're going to call this thing psi because we're going to start migrating this thing towards something that ultimately we will call the wave function, okay? And then you can imagine now we've got 100,000 different eigenstates. So I is a good label. So we'll count them 1, 2, 3, 4, 5, 6, 7, 8 to 100,000. And then each of those would have a little number alpha I. But now alpha I is in all these little positions along this axis, for example. So imagine we're starting to head towards this picture of a particle along an x-axis. So each of these is along some place. And so what we could do is actually start thinking, what I need to do is take a function, which is a sort of a proxy for my complex number, and just pick out which particular one I want, right? So if I want to know what the prefactor for particle at x equals 0, it would be psi at the lambda I that corresponds to x equals 0, right? And then to fully work out what's going on with those 100,000 eigenstates there, we basically add over all of them in the same way that we add over up and down when we're just dealing with this simple system at the front. The next step here really is to just now make infinite number of possible eigenvectors and values in here. And at that point, they become so close together and so continuous that it no longer makes sense to count them as, number one, number two, number three, because, there's like an infinite number of them. And this one is like a half infinity plus one, right? So what we tend to do there is make a jump to treating our complex number that's associated with every single particular eigenvector or all of our eigenvalues along here, and really just treat it as a continuous function, right? You can see we're already taking this step from going, discrete complex numbers to complex numbers that are just connected to a function where you just care about the position on that function. And this is a thing that ultimately in here we call the wave function. And I'll show you later on where the wave part of this just naturally pops out. Okay, by the time we get to the end of the second lecture, we'll have the de Broglie wavelength just pop out of the maths. Okay, so if we think about wave functions a little bit now, what I'm going to do here is start with this idea of being able to see the wave function as a traditional vector, in the sense that you take your x-axis, you chop it up into little pieces, and you ask, what is the complex prefactor for finding the eigenstate or the eigenvector where x is at 0, for example, and there would be a complex number attached to that you can extract the probability from, all right? Considering that as a vector, like which element do I pick, through to which way I think about this in terms of a function, we're going to kind of just move across from this line now, okay? So what I want to do here is start by considering, imagine that I've got all of these possible eigenvectors I can pop out, and I want to get the probability of one in particular. Okay, so if I think back to my spin up, spin down, this is sort of the question of asking, what if I've got some superposition state that's some mix of up and down, what is my probability of getting an up? Okay, so what I'm going to do here is go, I've got a whole pile of possible positions across here, infinite number of them. I want one particular position. What's my probability of getting that one particular position? Okay, and we'll do this starting from a sort of a vector spacey sort of direction and show that we end up with a formula that looks like it would be a function, okay? So what we're going to do here is get the probability of finding some particular eigenvalue lambda j amongst all the possibilities lambda I running through. I need some writing paper. And so what I've already done is written down what our state was from the last slide. Okay, so we've got this state psi that's basically the sum of all the possible complex prefactors times their eigenvectors all the way along. Okay, if we work out what this probability is, what we've got here, I can either do this by projection operators, or the other way of treating this is that I can take this element here on the right, know that the one on the left is just the complex conjugate of it, and so I can multiply whatever I get with this inner product on the right by its complex conjugate. Okay, we talked about this back when we did probabilities. So what we're going to do is calculate this thing. And I'm going to be interested in a particular lambda j that's different from lambda I, because I'm using lambda I as my summing index across the whole of this axis. Okay, so let's work our way through here. We've got lambda j psi is just going to be lambda j sum over I psi lambda I, like so. Okay, you'll remember that I can take the sum out the front, right? Because something multiplied by a sum is basically the sum of that thing multiplied by each of the elements. And as we saw in an earlier lecture, I can also take complex numbers out the front, because this thing psi lambda I is a complex number, not an operator. Okay, so this thing would end up being sum over I psi of lambda I. Take these things out the front and then bring the brackets together. So this would be lambda j in here, lambda I on the right. And of course, we know this thing, lambda j, lambda I, is really just an orthogonality relation, right? We've got an eigenvector lambda j and an eigenvector lambda I, and we're taking the inner product. So this thing's going to be delta ij, and we know that that delta ij equals 0 if I is not equal to j, and it's equal to 1 if I is equal to j. Okay, saw this one earlier. So what's going to happen is that we're going to be adding a whole pile of terms. Almost all of them I is not going to be equal to j, so that's going to be 0, and those terms are going to vanish. And we're going to be left with exactly one of them, which is the one where I is equal to j. What we're basically doing is taking a whole pile of values, I, and going, which is the jth one? That's the one we want. So that will be 1. The sum of one term is a term on its own. So this would actually be just psi of lambda j in the end, because that's the one we pick. Okay. And if you think now about what your psi lambda j is going to be, it's just the conjugate of that, right? That'll be a j. So this thing will just be psi of lambda j star, right? And so then if we work out what our probability is, we basically find that our probability is our psi of lambda j times our psi of psi star of lambda j. What we're taking is a function times its complex conjugate. And now if instead of thinking about, an eigenvector lambda I, what we do is we just go, every position x is an eigenvector, then and then just treat this thing as a function. What we're really doing is just saying the probability of finding our particle at position x is just our wave function psi of x times the conjugate of our wave function psi star of x. Okay, and many of you in your first year courses hopefully have seen for the first, at least for the first time, something that looks like this, right? You get probabilities by taking the wave function times its complex conjugate. This is where it pops out of. It's basically just taking the linear algebra that we had for a spin, adding an infinite number of observables, and just following across to functions, and you end up with something like that quite naturally popping out, mostly because what you need to do is take out the imaginary parts of your complex vector space before you translate back to your real world. Okay. So with that in mind, let me grab a couple of little mathematical ideas and rules in here to finish off this first half of the lecture. And then in the second half, we'll start to try and put some more flesh to the bones of this mathematically. So the way we handle this mathematically is we often associate the ket for psi with the wave function psi of x. And often you will see those two almost used interchangeably. And likewise, we associate the bra for the state psi with the conjugate of the wave function. And again, sometimes you'll see those two things almost used interchangeably, depending on which book or which person's doing the algebra and how tight or sloppy, like rigorous or loose they're being with the detail in their maths. We have now the idea that integrals replace sums, right? So we've gone from two states where we can just have a plus sign to many states where we would have a sigma to sort of an infinite number of states with a very tiny separation. And as you learn in high school, that is sort of the integral limit. So you switch from sums to integrals. We also have the idea that probability densities replace probabilities. I'll talk about that in a moment because I want to show a graph associated with it. And then the third one that we have is that our Kronecker deltas, so these things that we had where if the two indices are the same, they're equal to 1, and if the two indices are different, it's equal to 0, get replaced with things that we call Dirac delta functions. And I'll show you what one of those is in a moment. These delta functions in here basically mean that every distinct position x along an axis is basically a distinct eigenvalue or a distinct eigenvector for the system. And therefore, all of these positions are orthogonal to each other, right? We're now dealing essentially with an infinite dimensional Hilbert space with every possible position along the axis being an orthogonal axis. And at that point, if you can visualize that, you're probably a genius. Okay, so probability density. If you imagine back to spin up, spin down, we had a probability of half and a probability of half. And I always like to come in through that direction simply because probability is easier to think about. You kind of used to the idea that if you have a coin, it's a 50% chance of getting heads and a 50% chance of getting tails. If you now go to like a spin 1 system, you could imagine, it might be a third and a third and a third or something like that. If you've got a spin 3/2 system with 4 possible states, it might be a quarter and a quarter and a quarter, but all the way you're dealing with fractions, right? And so you'll remember just earlier on the paper, I actually calculated the probability of getting a particular eigenstate lambda j amongst all the lambda i's. The thing that I didn't finish in that calculation with was how small that is. It's actually really, really tiny. And so you end up with a number that's so small that it's actually, for all intents and purposes, meaningless. What we generally do is ask the question of, what sort of, how where are we going to find our particle within a certain width, right? Because, a particle might have a size, and so it's no point asking, whether its position is more precise to either the width of the particle or how well you could measure it. And so what we tend to do is ask the probability over some range, right? And so what we do there is then integrate this probability density over some range in here between A and B to get the probability of finding the particle in some position. Okay, hopefully you're familiar with probability density from your maths courses. If you're not, it's probably a good time to go back and just very quickly review how it fits together, because as you go on with wave functions, it becomes a fairly important concept. The next thing we need to deal with really quickly is orthonormality, okay? Both of these relations still hold. They just turn up in a slightly different form when you're dealing with functions compared to vectors. So let me deal with orthogonality first. You'll remember that we had this idea with our spin that you can have an up and a down, and if you take the inner product of up and down, you will get 0, okay? You have the same idea when you deal with functions, but you've got to think about it slightly differently. The way I always like to think about it is if you think about up, there's an alpha up attached to that up. And if you think about down, there's an alpha down attached to that down. And those are two different complex numbers, right? The alpha up is distinctly connected to the up. The alpha down is distinctly connected to the down. Now let's imagine that you've got a very, very large number of states of eigen vectors along an axis, right? One of the situations you can measure is, say, the particle at position x equals 1. And the other thing that you might measure is particle at position x minus 1. Those would correspond to two very different functions. One is a function where it's basically 0 all the way along, and then there's a little blip in the complex number at the position 1 and then 0. And then the other one, minus 1, would be essentially the complex number or the complex function is 0 all the way along until the minus 1. There's a little blip, and then it's 0 all the way along, right? And these are two distinct functions, one that has a blip at minus 1 and one has a blip at plus 1. What you then need to do is take those two complex numbers. If you think about taking the inner product between the up state and the down state, what you're actually doing is taking, let me actually write this for a second then. If you take something that looks like this, what you're actually doing here is taking a vector that looks like 1, 0, I'll leave the conjugates off, and 0, 1 here. And then you're basically taking the sum of the elements when you do the vector product, right? Remember, you do 1 times 0 plus 0 times 1. And so what you're doing is you're sort of going, I'm going to take the first element for one vector times the first element for the other vector, the first element for the second element for the first vector times the second element for the second vector. And if you imagine now taking longer vectors, imagine you had like a vector that's n long for your first state and n long for your second. It would be the first times the second times the second, plus the third times the third, plus the fourth times the fourth, plus the fifth times the fifth, and work your way through that whole thing to get the inner product, right? If you now think about this in terms of functions, what you've got is this big string of numbers for one, this big string of numbers for the second one, and what you need to do is take the first number times the first number, the second number times the second number, the third number times the third number, and keep going all the way along. You get this blip on this one, you get this blip on this one, and you go all the way to the end. What that is mathematically is taking the function for the first of these functions, which we'll call psi here, the function for the second of these functions, which we'll call phi here, and basically adding all the terms together over their entire range as the product, and doing that from one end to the other, right? And because it's a function that you can allow to go from minus infinity to plus infinity, you're basically doing an integral over the entire function. Okay, so this expression we have here with this integral is basically just taking the infinite element limit of an inner product. And of course, that thing ends up 0 because the point where there's the blip in the -1 function is 0 on the other function and vice versa. And so it ends up that with the product being 0 absolutely everywhere. And those are two distinct orthogonal states. Okay. In a similar way, we have a normalization condition, right? And basically this corresponds, if you think back to our spin, we would take either inner product of up and up or inner product of down and down, and we would get 1, right? So what we would be doing there is taking a vector that looks like 1, 0, 1, 0, and so we'd have 1 times 1 plus 0 times 0 is equal to 1, right? Take the same logic for that. Now apply it to a function. What we will be doing is taking the same state and multiplying it by its complex conjugate, right? Up times up conjugate is the same as ket up times bra up. So what we would be doing is now working our way along, and the place where the blip is, say it's at 1, would be the same on both curves. All we've done is just change the sign of the imaginary element by taking the conjugate. And now we would do the same thing. We would add all the way along here. And in much the same way, when we take up times up, we get 1 times 1 plus 0 times 0. We'd get zeros all the way along here that multiply with each other. Where the blip is the same for both functions. So that multiplies to a number that's not 0. And then we keep going all the way along. Okay, and then what we could do is divide that integral by its own value to normalize this thing back to 1, because what we require in the end is that all probabilities come out as 1. So the idea of normalization that we have in quantum mechanics, this idea that the length of a vector, that a basis vector is 1, so the probabilities make sense, ends up being that if we take the product of a wave function and its complex conjugate over an integral over the entire space, that will be equal to 1. And if it isn't, we will do whatever we have to do to make that 1 so that the probability that we get from our probability densities ends up being a sensible number between 0 and 1. Okay? So all we've done is just basically taken two relations that we had and extended them into a functional form. And then the last thing I want to deal with before the break is the Dirac delta function. This will be the first time you see it. I don't expect you to 100% understand this function today. It's one of those things that takes a little bit of time in quantum mechanics to get to grips with. And when you do Fourier transforms later on, you will start to see how the delta function works in a bit more detail. Basically what it is it's a function where you run along some axis x, and it has a value of 0 everywhere except for where x is equal to x dash. And at that point, x equals x dash, it has infinite value. Okay, so it basically comes along. It's this blip I was talking about, basically. It comes all the way along. There's a blip at the point where you're at x dash, and then it's nothing all the way along. The interesting thing about this curve or this function is that it's normalized, right? So it's 0 everywhere, it's infinite at one point, yet if you take the integral of that function over the entire space, the area under that function is equal to 1. It's a normalized function, okay? In a graphical form, it basically just looks like zeros everywhere and a blip in the middle. In this particular graph, it's for x dash equals 0. And its job mathematically is to pick out states in much the same way that the Kronecker delta does, okay? I've got a star on this. I'm going to consider this to be an advanced point for now. Later on, you will be expected to understand this in your courses. But for my half of the course, I'm just going to leave this as something for you to think about a little bit. What it does is it exists to pick states. And so if you think about our Kronecker delta, what it really does is give you a value of 0 unless this state here, x, is basically equal to the state a, right? What your Dirac delta function does from a functional perspective is if you take the product of f of x and a delta function x minus a, it will pick out the function at the point A, or the value of the function at point A. That is an advanced point, okay? For a lot of you, that will fly over your heads the first time you see it. I remember as an undergraduate, the first time I saw it, it went straight over my head as well. It takes a while to get to grips with, but I want to point it out so you see it there. I think at this point I will take a break, and then in the second half I'm going to come back and basically start looking at how operators look like in the functional version of quantum mechanics.